Okay, so this video is going to be all about the conservation of energy and how you use the conservation of energy with the energy information we've already gathered. So, the law of conservation of energy says energy cannot be created or destroyed, but can just be transferred from different forms. So really, the three main things, it can't be created, can't be destroyed, and it's only converted between different things, which means it can become in different it can go to different forms, like kinetic energy become potential energy. It could also change into like not only mechanical energy, but it could change into heat and sound. Okay, so the total energy of a system never changes, it just changes form. Okay, so a couple reminders on things. Okay, we have kinetic energy, 1/2 mv squared. We have gravitational potential energy, mgy times your height. And we have elastic potential energy, so stored springs, 1/2 kx squared, where k is your spring constant. Okay, so keep those in mind. All right, so we have a system consisting of an object and the surface it slides on. It'll gain heat energy if there's friction. So the change in what we call change in thermal energy is your friction force times the distance that it slides, often just like work. Okay, and we look at all for an isolated system. Okay, for one system in particular, the final total energy needs to equal the initial total energy. Okay. So we can use the law of conservation of energy to look at before and afters. So if you have a change in energy, remember work is equal to how much energy you have that you change. So the total change in energy is work. Initially, so for your final kinetic, gravitational, static kinetic, or static potential, and heat energy before has to equal afterwards. Okay. So in an isolated system, if there's no work done on an object where it's not gaining or losing any energy, the energy before has to equal the energy at the beginning. Okay. All right, so again, here we go. If we have an isolated system, so the ball going to the earth, okay, there's no external force to do the work on this, so work is equal to the force on the ball. Object sliding down a ramp. The external force the ramp exerts on the object is perpendicular to the motion, so really the normal force does no work. Okay. Object compressing a spring. Okay, the forces between them are internal forces, so we're not even actually really looking at a force done on the object. An object sliding along the surface with friction. Okay, the block on the surface interacts via kinetic friction forces, so friction is doing there. But the forces are internal into the system, they're not being acted on the system. Okay. So we're going to look at some more sample problems here. So a car sits at the top of a hill. Okay, so a small push sends it not rolling down the hill. After its height is dropped by 5 meters, it is moving at a good speed. Right, we're going to figure out the equation and what energy transformations have taken place. Okay, so if we look at this, the system is just what's acting on the car, and the small push indicates there's initial kinetic energy. Really, there's no initial kinetic energy other than the initial push, because as it goes down the hill, its potential is going to be converted to kinetic energy. Okay. So again, the bottom of the hill is going to be 0. So we say that our kinetic energy final plus gravitational potential energy final is equal to kinetic energy initial plus gravitational potential energy initial. We have no initial kinetic energy. We have no final gravitational potential energy because it's going to the ground, to the bottom. So the kinetic energy final is equal to the initial potential energy. Okay, and in both these cases, the masses cancel out because kinetic energy has mass, potential energy has mass, and since it's kinetic energy final equals initial potential energy and the mass remains constant, the mass can cancel out. So you're left with V, because you're left with essentially 1/2 mv squared is equal to GH, gravitational acceleration times height. Okay. So we have this. And yeah. Okay. So car slides down a slide, our child slides down a slide with a constant speed of 1.5 meters per second. The height of the slide is 3 meters. Again, we're going to figure out the energy. Okay. So the system is a child. Because the movement is at a constant speed, work done is on the child by the slide. So we have all of the initial and potential kinetic energy equation written down here. So because the speed is constant, the kinetic energy is constant, and the initial gravitational potential is converted to the heat energy. So again, we're looking at Katie tries a water slide. It looks like this. Starting point is 9 meters above the ground. She has an initial velocity of 2 meters per second. We're going to look for how fast she will be going at the bottom of the slide. Really, if you think about it, all of her energy is at the top is going to be kinetic energy at the bottom. Okay, so we look at this. We have kinetic energy plus gravitational potential energy final equals kinetic energy initial plus gravitational potential energy initial. Or here's your formula. Okay. So y final is 0. That leaves us with this. Okay. So if we solve for VF, we end up rearranging the equation. Her final velocity is 13 meters per second. Okay. Going again, because we have our final energy is equal to initial energy. We have no initial, or we have no final height, so we have no final gravitational potential energy. Okay. All right, so we're going to look at another problem. So Monica's pulling her daughter Jessie in the bike trailer. Combined, they have a mass of 25 kilograms. Monica starts up a 100-meter long slope that is 4 meters high. On the slope, the bike pulls on the trailer with a constant force of 8 newtons. They start off with at the bottom of the slope with a speed of 5.3 meters per second. What's their speed at the top? Okay. So here's what we have. We know before the y initial height is 0. They have initial velocity of 5.3 meters per second. They're traveling a distance of 100 meters with a force applied of 8 newtons. With the mass that she's carrying of 25 newtons. We want to figure out what the final velocity is, knowing that she's gone up 4 meters. Okay, so we're going to need the full version of this, including we're going to have to look at it in terms of work. Okay, so again, the final energy is going to be our kinetic energy final plus gravitational potential energy final is equal to kinetic energy initial plus potential energy initial plus work. She's done work on the object. She's put energy into it, so the work has been added to it. So we have to make the equation look like this, which creates the equation that looks like this. Okay. So our initial y is 0. And work is force times distance. We can rearrange to solve for the final speed. Okay. Because the reason this m is here is because it's been taken out of the other 3 parts of the equation. So 5.3 meters per second and square that's your initial velocity. 2 times g, y final, that's your final height, plus 2 times the force times the distance divided by your mass take the square root of all this, you're going to get 3.7 meters per second. Okay. So the work was added, so you have to add that to your conservation of energy equation. Okay. All right. So that's the end of this video. Please do the Google form below and ask any questions if need be. And we'll see you in class.